Hey guys, today I'm going to be tackling these networking concepts from the TryHackMe Cybersecurity 101 learning path. So yeah, this is kind of a new module, I think. Yeah, 13 days ago. So let's go through this. This should serve as a good reminder of how networking concepts uh, basically work, right? Okay, let's go. Networking concepts. Learn about the ISO OSI model and the TCP/IP protocol suite. Have you ever wondered why you need an IP address to access the internet? Is it true that an IP address can uniquely identify the user? Are you curious to learn what the life of the packet looks like? If the answer is yes, let's dive in. This room is the first room in a series of 4 rooms dedicated to introducing the user to vital networking concepts and the most common networking protocols. Networking concepts, this room. Okay, next. Networking essentials, core protocols, secure protocols are the next modules. Room prerequisites. This room expects that you know terms such as IP address and TCP port number. However, we don't expect that the reader is able to explain such terms in proper technical depth. If you're unfamiliar with these terms, please consider joining the pre-security path. Learning objectives. By the time you finish this room, you will have learned about the following: ISO OSI network model, IP addresses, subnets, and routing, TCP, UDP, and port numbers, how to connect to an open TCP port from the command line. Get your notepad ready and let's begin. Okay, let's go to the OSI model. Yeah. Before we start, we should note that the OSI model might initially seem complicated. Don't worry if you encounter cryptic acronyms, as we provide examples of the OSI model layers. We are sure that by the time you finish this module, this task will feel like a piece of cake. The OSI model, the Open Systems Interconnection Model, is a conceptual model developed by the International Organization for Standardization that describes how communications should occur in a computer network. In other words, the OSI model defines a framework for computer network communications. Although this model is theoretical, it is vital to learn and understand as it helps grasp networking concepts on a deeper level. The OSI model is composed of 7 layers: the physical layer, the data link layer, network layer, transport layer, session layer, presentation layer, and application layer. The numbering starts with the physical layer being layer number 1, while the top layer, the application layer, is layer number 7. To help you remember the layers from bottom to top, you can use a mnemonic such as please do not throw spinach pizza away. Please do not throw spinach pizza away. Okay. You can check the internet for easy to remember acronyms. If this helps you memorize them, remembering the OC model layers with their layer numbers is important. Otherwise, you will struggle to understand terms such as layer 3 switch or layer 7 firewall. Okay, layer 1, physical layer. The physical layer, also referred to as layer 1, deals with the physical connection between devices. This includes the medium, such as wire, and the definition of the binary digits 0 and 1. Data transmission can be via an electrical, optical, or wireless signal. Consequently, we need data cables or antennas, depending on our physical medium. In addition to Ethernet cable shown in the illustration below, an optical fiber cable. Examples of the physical layer medium include the Wi-Fi radio bands, the 2.4 gigahertz band, and the 5 gigahertz band, and the 6 gigahertz band. Layers 2. Data link layers. The physical layer defines a medium to transmit our signal. The data link layer, or layer 2, represents the protocol that enables data transfer between nodes on the same network segment. Let's put it in simpler terms. The data link layer describes an agreement between different systems on the same network segment and how to communicate. A network segment refers to a group of network devices using a shared medium or channel for information transfer. For example, consider a company office with 10 computers connected to a network switch. That's a network segment, right? Examples of layer 2 include Ethernet 802.3 and Wi-Fi 802.11. Ethernet and Wi-Fi addresses are 6 bytes. Okay. Their address is called a MAC address, where MAC stands for Media Access Control. They are usually expressed in hexadecimal format with a colon separating each 2 bytes. The 3 leftmost bytes identify the vendor. So vendor who built the network interface, in this instance Intel. Unique address of the network interface, the last 3, right? We expect to see 2 MAC addresses in each frame in real network communications over Ethernet or Wi-Fi. The packet in the screenshot below shows the destination data link address, MAC address. Okay, yeah, highlighted in yellow. Okay, The source data link MAC address is highlighted in blue. Yeah. The remaining bits show the data being sent. Yeah. Network layer. Okay, the data link layer focuses on sending data between two nodes on the same network segment. The network layer is concerned, or layer 3 is concerned with sending data between different networks. In more technical terms, the network layer handles logical addressing and routing, finding a path to transfer the network packets between the diverse networks. In the data link layer, we gave an example of one company office with 10 computers, where the data link layer is responsible for providing a connection between them. Let's say that this company has multiple offices distributed across various cities, countries, or even continents. The network layer is responsible for connecting the different offices together. Okay. The network below shows that computer A and B are connected, although on different networks. You can also notice two paths connecting the two computers. The network layer will route the network packets to the path it deems better. Okay. Yeah. Examples of the network layer include the Internet Protocol or IP, Internet Control Message Protocol (ICMP), and Virtual Private Network (VPN) protocols such as IPsec and SSL TLS VPN. Okay, the layer number 4 is transport layer. Layer 4, the transport layer enables end-to-end communication between running applications on different hosts. Your web browser is connected to the TryHackMe web server over the transport layer, which can support various functions like flow control, segmentation, and error correction. Examples of layer 4 are transmission control protocol, TCP, and user datagram protocol, UDP. Okay. Okay, so this is between running applications on different hosts. And then the session layer. The session layer is responsible for establishing, maintaining, and synchronizing communication between applications running on different hosts. Establishing a session means initiating communication between applications and negotiating the necessary parameters for the session. Data synchronization ensures that data is transmitted in the correct order and provides mechanisms for recovery in case of transmission failures. Examples of the layer are network file system. Yeah, this is a way to transfer files, and remote procedure call (RPC). 6. Presentation layer. The presentation layer ensures that data is delivered in a form the application layer can understand. Layer 6 handles data encoding, compression, and encryption. An example of encoding is character encoding, such as ASCII or Unicode. Various standards are used at the presentation layer. Consider the scenario where we want to send an image via email. First, we use JPEG, GIF, and PNG to save our images. Furthermore, although hidden from the user by the email client, we use MIME, multi-purpose internet mail extensions, to attach the file to our email. MIME encodes a binary file using 7-bit ASCII characters. And then the last layer, the application layer. The application layer provides network services directly to end-user applications. Your web browser would use the HTTP protocol to request a file, submit a form, or upload a file. The application layer is the top layer, and you might have encountered many of its protocols as you use different applications. Examples of layer 7 protocols are HTTP, FTP, DNS, POP3, SMTP, and IMAP. Don't worry if you're not familiar with all of them. Summary. Reading about the ISO OSI model for the first time can be intimidating. However, it becomes easier as you progress in your study of networking protocols. To help with your studies, we have summarized the ISO OSI layers in the table below. Okay. Which layer is responsible for connecting one application to another? I think it would be layer 4. Yes. Which layer is responsible for routing packets to the proper network? That would be layer 3, I think. Yeah. In the OSI model, which layer is responsible for encoding the application data? Encoding. Okay. The layer 6. And then which layer is responsible for transferring data between hosts on the same network segment? The first one. No, layer 2. Yeah. TCP IP model. Okay, now that we have covered the conceptual ISO OSI model, it's time to study an implemented model, the TCP IP model. TCP IP stands for Transmission Control Protocol, Internet Protocol, and was developed in the 1970s by the Department of Defense. I hear you ask why DoD would create such a model. One of the strengths of this model is that it allows a network to continue to function as part of it are out of service. For instance, due to a military attack. This capability is possible in part due to the design of the routing protocols to adapt as the network topology changes. In our presentation of the ISO OSI model, we went from bottom to top, from layer 1 to layer 7. In this task, let's look at things from a different perspective, from top to bottom. From top to bottom, we have application layer, the OSI model application, presentation, and session layers. Layers 5, 6, and 7 are grouped into the application layer in the TCP/IP model. Transport layer, this is layer 4. Internet layer, this is layer 3. The OSI model's network layer is called the internet layer in the TCP/IP model. And link layer, this is layer number 2. The table below shows how TCP/IP models layers map to the ISO OSI model layers. Okay. Yeah. Okay. Many modern networking textbooks show the TCP/IP model has 5 layers instead of 4. For example, in computer networking, a top-down approach 8th edition Corrosion Rose describes the following 5-layer internet protocol stack by including the physical layer. In the following tasks, we will cover the IP protocol from the internal layer and the UDP and TCP protocol from the transport layer. To which layer does HTTP belong in the TCP/IP model? Application layer. How many layers of the OSI model does the application layer in the TCP/IP model cover? How many layers? I think it's 5, right? Then according to you, it's 4. What? Oh, sorry, 3. Okay, next one. IP addresses and subnets. When you hear the word IP address, you might think of an address like this one, yeah, or something less common such as this one. In both cases, you're right. Both of these are IP addresses, IPv4, IP version 4 addresses to be specific. Every host on the network needs a unique identifier for other hosts to communicate with them. Without a unique identifier, the host cannot be found without ambiguity. When using the TCP/IP protocol suite, we need to assign an IP address for each device connected to the network. One analogy of an IP address is your home postal address. Your postal address allows you to receive letters and parcels from all over the world. Furthermore, it can identify your home without ambiguity. Otherwise, you cannot shop online. As you might already know, we have IPv4 and IPv6, IP version 6. IPv4 is still the most common, and whenever you come across a text mentioning an IP without the version, we expect them to mean IPv4. So what makes an IP address? An IP address comprises 4 octets, 32 bits, being 8 bits. An octet allows us to represent a decimal number between 0 and 255. An IP address is shown in the image below. In the first octet, yeah, at the risk of oversimplifying things, the 0 to 255 are reserved for the network and broadcast addresses, respectively. In other words, 192.168 is the network address, while this one is a broadcast address. Sending to the broadcast address targets all the hosts on the network. With simple math, you can conclude that we cannot have more than 4 billion unique IPv4 addresses. If you're curious about the math, it is approximately 232 because we have 32 bits. This number is approximate because we didn't consider network and broadcast addresses. Okay, looking up your network configuration. You can look up your IP address on the MS Windows command line using the command ipconfig. On Linux and Unix-based commands, you can issue the command ifconfig or IP address show, which can be typed in IPAS. In the terminal window below, we show ifconfig. Yeah, the terminal output above indicates the host. This is the IP address. Yeah. And then the subnet mask. Yeah. And then the broadcast address is this one. Okay. Right. Let's use IPAS to compare how the network card IP address is presented. Okay, it's different. The terminal output above indicates the following. The host laptop IP address is this one on port 24. Why 24? Oh, okay, it's not port. Sorry. The broadcast address is this one. Okay. If you are wondering, a subnet mask of 255.0 can also be written as 24. 24 means that the leftmost 24 bits within the IP address do not change across the network. The subnet. In other words, the leftmost 3 octets are the same across the whole subnet. Therefore, we can expect to find addresses that range from 192.168.66.1 to 662.254, right? Similar to what was mentioned earlier, 192.660 and this one are the network and broadcast addresses respectively. Yeah. Private addresses. As we're explaining IP addresses, it is useful to mention that for most practical purposes, there are 2 types of IP addresses. public IP address and private IP address. RFC 1918 defines the following three ranges of private IP addresses. Yeah, okay. We presented earlier an analogy stating that a public IP address is like your home postal address. A private IP address is different. The original idea is that it cannot reach or be reached from the outside world. It is like an isolated city or a compound, where all houses and apartments are numbered systematically and can easily exchange mail with each other, but not with the outside world. For a private IP address to access the internet, the router must have a public IP address and must support network address translation (NAT). At this stage, let's not worry about understanding how NAT works, as we will revisit it later in this module. Before moving on, I recommend memorizing the IP address ranges, otherwise you might see an IP address such as 10 or this one and try to access it from a public IP address. We wouldn't want that because we wouldn't be able to, right? Routing. A router is like your local post office. You hand them the mail parcel and they would know how to deliver it. If we dig deeper, you might mail something to an address in another city or country. The post office will check the address and decide where to send it next. For example, if it is to leave the country, we expect one central office to handle all shipments brought. In technical terms, a router forwards data packets to the proper network. Usually, a data packet passes through multiple routers before it reaches its final destination. The router functions at layer 3, inspecting the IP address and forwarding the packet to the best network router so the packet gets closer to its destination. So it's web mobile user, router, and then it gets to the web server, and same with the office user, right? Which of the following IP addresses is not a private IP address? Not a private. It's this one, 69.147.197. Yeah. Which of the following is not a valid IP address? Not valid. Okay. 25. This one, because it's up to 255. Remember? Yeah. UDP and TCP. What do we have here? The IP protocol allows us to reach the destination host on the network. The host is identified by its IP address. We need protocols that would enable processes on network hosts to communicate with each other. There are two transport protocols to achieve that, UDP and TCP. UDP, Users Diagram Protocol, allows us to reach a specific process on this target host. UDP is a simple connectionless protocol that operates at the transport layer, layer 4. Being connectionless means that it does not need to establish a connection. UDP does not even provide a mechanism to know that the packet has been delivered. An IP address identifies the host. We need a mechanism to determine the sending and receiving process. This can be achieved by using port numbers. A port number uses 2 octets. Consequently, it ranges from 1 and 65,535. Port 0 is reversed. The number 65535 is calculated by the expression 2 to 16 minus 1. A real-life example similar to UDP is the standard mail service, with no delivery confirmation. In other words, there is no guarantee that the UDP packet has been received successfully. Similar to the case of sending a parcel using standard mail with no confirmation of delivery, in the case of standard mail, it means a cheaper cost than the mail delivery options with confirmation. In the case of UDP, it means better speed than a transport protocol that provides confirmation. But what if we want a transport protocol that acknowledges received packets? The answer lies in using TCP instead of UDP. Okay, there's a difference between them too. See? So TCP Transmission Control Protocol is a connection-oriented transport protocol. It uses various mechanisms to ensure reliable data delivery, same but different processes on the network hosts. Like UDP, it is a layer 4 protocol. Being connection-oriented, it requires the establishment of a TCP connection before any data can be sent. In TCP, each data octet has a sequence number. This makes it easy for the receiver to identify lost or duplicated packets. The receiver, on the other hand, acknowledges the reception of data with an acknowledgement number specifying the last received octet. A TCP connection is established using what's called a three-way handshake. 2 flags are used: SYN, synchronize, and acknowledgement. The packets are sent as follows. SYN packet. The client initiates the connection by sending a SYN packet to the server. The packet contains the client's randomly chosen initial sequence numbers. SYN acknowledge packet. The server responds with to the SYN packet with the SYN acknowledge packet, which adds the initial sequence number randomly chosen by the server. Acknowledge packet. The three-way handshake is completed as the client sends back an ACK packet to acknowledge the reception of the SYN ACK packet. Okay, so it's like a handshake. Similar to UDP, TCP identifies the process of initiating or waiting, listening for a connection using port numbers. As stated, a valid port number ranges between 1 and 65,535 because it uses 2 octets and port 0 is reversed. Which protocol requires a three-way handshake? TCP. What is the approximate number of port numbers in thousands? The approximate number of port numbers in thousands, 65. Yeah. Encapsulation. Before wrapping up, it is crucial to explain another key concept, encapsulation. In this context, encapsulation refers to the process of every layer adding a header, and sometimes a trailer, to the received unit of data and sending the encapsulated unit to the layer below. Encapsulation is an essential concept as it allows each layer to focus on its intended function. In the image below, we have the following 4 steps. Application data. It all starts when the user inputs the data they want to send into the application. For example, you write an email or an instant message and hit the send button. The application formats this data and starts sending it according to the application protocol used, using the layer below it, the transport layer. Transport protocol segment or the datagram. The transport layer, such as TCP or UDP, adds the proper header information and creates the TCP segment or UDP datagram. This segment is sent to the layer below, the network layer, network packet. The network layer, the internet layer, adds an IP header to the received TCP segment or UDP datagram. Then this IP packet is sent to the layer below it, the data link layer. Data link frame, the Ethernet or Wi-Fi receives the IP packet and adds the proper header and trailer, creating a frame. Okay. We start with application data. At the transport layer, we add a TCP UDP header to create a TCP segment or UDP datagram. Again, at the network layer, we add the proper IP header to get an IP packet that can be routed over the internet. Finally, we add the appropriate header and trailer to get a Wi-Fi or Ethernet frame at the link layer. Sweet. The process has to be reversed on the receiving end until the application data is extracted. The life of a packet. Based on what we have studied so far, we can explain a simplified version of the packet's life. Let's consider the scenario where you search for a room on TryHackMe. On the TryHackMe search page, you enter your search query and hit enter. Your web browser using HTTPS, which is on the top layer, the layer 7, prepares an HTTP request and pushes it to the layer below, the transport layer. The TCP layer needs to establish a connection via a three-way handshake between your browser and the TryHackMe web server. After establishing a TCP connection, it can send the HTTP request contained in the search query. HTTP segment created is sent to the layer below it, the internet layer. The IP layer adds the source IP address, your computer, and the destination IP address, the IP address of the TryHackMe web server. For this packet to reach the router, your laptop delivers it to the layer below, the link layer. Depending on the protocol, the link layer adds the proper link layer header and trailer, and the packet is sent to the router. The router removes the link layer header and trailer, inspects the IP destination among other fields, and routes the packet to the proper link. Each router repeats this process until it reaches the router of the target server. This step will then be reversed as the packet reaches the router of the destination network. As we cover additional protocols, we will revisit this exercise and create a more in-depth version. Okay, on a Wi-Fi, within what will an IP packet be encapsulated? A Wi-Fi. Yeah, it's a frame, right? Yeah. What do you call the UDP data unit that encapsulates the application data? Datagram. What do you call the data unit that encapsulates the application data sent over TCP? That is a packet. No, sorry. What's that? Segment. Then Telnet. Okay. Here we have to start a machine. Sure. Start by pressing the start button on the top. Yeah. Okay. Give them 2 minutes each to properly boot up. Most of the machines are ready. What? Ready? We need to start the terminal on the attack box to experiment with Telnet. The Telnet teletype network protocol is a network protocol for remote terminal connection. In simple words, a Telnet client allows you to connect and communicate with a remote system and issue text commands. Although initially it was used for remote administration, we can use Telnet to connect to any server listing on the TCP port number. On the target virtual machine, different services are running. We'll experiment with 3 of them. Echo server. This server echoes everything you send it. By default, it lists on port um, on port 7, right? So I just want to check where will I have this machine. Let's split this. This is the blue show split. Yeah, we have that. And then okay. Okay, already started the attack box. Okay, so we're gonna be, okay, daytime server. This server listens on port 13 by default and replies with the current date and time. Web HTTP server. This server listens on TCP port 80 by default and serves web pages. Before continuing, we should mention that the echo and daytime servers are considered security risks and should not be run. However, we started them explicitly to demonstrate communication with the server using Telnet. In the terminal below, we connect to the target VM at the echo server's TCP port number 7. To close the connection, press Ctrl on the key simultaneously. Okay, Telnet this, then we should be able to send text. We use Telnet to connect to the daytime server listening port 13. We noticed that the connection closes once the current date and time are returned. Yeah. Okay. Okay, finally, let's request a web page using Telnet. After connecting to port 80, you need to issue the command get HTTP 1.1 and identify the host where anything goes, such as host telnet.thm. Next, you need to press enter twice so your last input line is a blank line. The output below shows the exchange the page has been redacted. You may have to press enter after sending information in case you don't get a response. Okay, just tell them to connect to the web server on this one. Okay. Can I ping? Yeah, received. So if I use Telnet to connect to the web server on the web server, right? So it's 10.20.172 and the web server is in port 80. Yeah. What is the name and version of the HTTP server? So then I have to get UDP 1.1 by command, but some tone belt commands. Come on. Okay, Telnet. Yeah, Telnet this, and then try Telnet. Yeah, escape hi, body command. What commands should help? Oh yeah, okay. Close. Display operating parameters. Yeah, no. What do I want to check? Ah, thanks. To connect to the web server on this, yeah, what is the name and version of the HTTP server? Where do I check that out? On send quit, mode, display operating parameters, mode, toggle, environment, Telnet display, interrupting one show options, processing, echo, escape, grayscale nets. Oh, connection closed. Okay. Let's get a hint. Note that you need to press enter twice after typing the host, and the answer should be in the format name version. After typing the host. Oh yeah, okay. What is the name, version, and version of the HTTP server? Oh yeah, okay, got it. Okay. Yeah, we got it. Yeah, okay. What flag did you get when you viewed the page? What flag? Was I supposed to see a flag? I didn't see no flag. Check. 404 by request, transition. It should be with THM, right? What flag did you get when you viewed the page? When I viewed the page? What do you mean when I viewed the page? Oh, you meant this, right? Okay, we got it. Now, next, in this room, we covered the ISO OSI model and TCP IP models, comparing and contrasting the two. We also covered IP addresses and subnets, briefly explaining routing. Furthermore, after diving into TCP and UDP, we explained encapsulation. For demonstration purposes. We use Telnet to talk to different servers over TCP. Now that you have finished networking concept, it is time to join networking essentials. Okay, this should be it. Thank you guys for sticking up me. It was a good learning path. Yeah, networking concepts. Yeah, good review of networking concepts. All right, see you guys.